Right, now the first speaker is Franziska Lindner from, let me see, interesting, Institute of Stochastic, Department of Mathematics. But where is Institute?
Karlsruhe Institute of
Oh, I see, right. So, and she's going to talk about local moving Fourier-based bootstrapping.
Thanks. Figure out how to extend the TFT bootstrap to a locally stationary time series. Well, that was my working hypothesis when I started my thesis some years ago. And at that point in time, I did not know anything about TFT bootstrap or local stationarity. And I think you can imagine how happy I am now that I can present to you the moving Fourier transformation, which is the central concept to our solution to this problem. And, well, this work is joint work with Claudia Kirch from the KIT. And first of all, we are going to look at the moving Fourier transformation. We'll then discover what properties those new coefficients have. Then, after looking at some existing bootstrap methods for locally stationary time series, I'm going to introduce you to our moving TFT bootstrap. And this kind of bootstrap is also used to, well, numerically efficiently construct not only pointwise, but uniform confidence bands. And I really hope that in the end of my talk, all of you share at least a little bit of my affection for this moving Fourier transformation. Well, let's start with the moving Fourier transformation. I'm a friend of keeping it nice and simple, and therefore we're going to start looking at a locally stationary time series of length 14. Locally stationary tells us it's basically stationary in a small environment. And the radius of this environment in our example equals 3. Lambda j are the Fourier frequencies. And we can thus assume that this stretch of data is basically stationary, centered around x4. And, well, we apply the usual Fourier transformation on this stretch of data and get the first Fourier coefficient from that. Well, for the second Fourier coefficient, we do not use that green stretch of data, but instead what we do is we move one step to the right and use that red stretch of data to get the second Fourier coefficient. Well, and as the green and the red stretch only differ by the very, very first and very last observation, heuristics are that basically the statistical properties of those two Fourier coefficients should be the same. And this is the principle of the moving Fourier transformation. And if we go on shifting and transforming, you can see that the frequencies will eventually start repeating themselves. And in order to have the Fourier coefficients, the corresponding ones, distinguishable, we introduced that new way of indexing, taking the central observation of that stretch, that is x4 in this example, dividing it by 3, which is our m, and then we use the remainder to index the frequency, same here, and we used this multiple of m as a superscript here. And if we continue doing that, we get the following sequence of Fourier frequencies. Well, formally, the definition of this moving Fourier transformation is like this. Mod is just basically a modular m operator, and this diff k is caring for those ascending superscripts up here. Okay, so now look at this Fourier coefficient. All this diff and mod notation tells us that this corresponds to k equal to 7. So we are at time k equal to 7, which means that this Fourier coefficient comes from the stationary environment of the observation x7. Well, but when we're interested in what happens to the time series at time 7, we don't just want one Fourier coefficient, do we? We want a whole set of Fourier coefficients. And this is basically what we do. We take the coefficient and grab the neighboring ones. And I don't know whether it's possible to see, but we have lambda 3 here, lambda 1, and lambda 2, and they are not in the right order. So we simply do some rearranging, and these resulting coefficients are what we call it the local moving Fourier coefficients at time 7. So here we can actually see what time they refer to. Well, does that all make sense from a theoretical point of view? To answer that question, we're going to look at the properties. The new Fourier coefficients are centered. Concerning the variance, we have that the local moving Fourier coefficient at time ut, frequency lambda L, asymptotically equals 2 pi times the time-varying spectral density at exactly that time and that frequency. And this convergence is uniform in time and frequency. Well, we also derived that very neat relation between the local moving Fourier coefficient of the locally stationary time series and the coefficient of the generating IID white noise of the time series, plus some remainder, but this remainder goes to 0 in L4, again uniformly in time and frequency. And if we additionally have this summability assumption of the coefficients of the stationary approximation, we even get a rate of 1 over m squared. Concerning the covariance of two different Fourier coefficients at the same time ut, we have that it goes to 0. And L and J are in between 1 and m. But now we have this set A1 here. What is A1? A1 basically excludes just some very few of those constellations. And we need A1 because we have the following problem. Remember the initial sequence of Fourier frequencies. And we have a break in the superscripts right here. Now, if one of the Fourier coefficients is on the left side of the break, one is on the right side, and they're not sufficiently far away from that break, the problem occurs. And we don't get that the covariance goes to 0. Well, but the set where the problem occurs, the cardinality of that set, goes to 0 as m goes to infinity. We've also studied covariances of those coefficients at different points in time, and we were able to also analyze the second order properties of moving versions of the spectral mean statistics. Okay, so now let's go down to some bootstrapping. There are basically 4 main methods of bootstrap procedures for locally stationary time series. There's one by Paparoditis and several others, who's just doing a local block bootstrap in the time domain. There's an extension of the autoregressive aided periodogram bootstrap by Kreis and Paparoditis. They start out in the time domain, apply a local ARC bootstrap, use some local Fourier transformation, and then add some local non-parametric correction. And in the end, they have bootstrap replicates of the periodogram ordinates. Well, what's special about the third method is that it actually enables to go back and forth between time and frequency domain. It's called local wild hybrid bootstrap by Kreis and Paparoditis. They use a special wild hybrid wild bootstrap here, then globally Fourier transform the results, do a local correction in the frequency domain, and then go back all the way. And our new moving TFT bootstrap is also able to do this going from time to frequency to time domain. It uses the moving Fourier transformation, and also a new aspect is that we use bootstrap methods in the frequency domain. Well, and I know we're all curious to see how it really works, so let's take a look at it. Well, first of all, we start with a time series x1 up to xt, then transform it using the moving Fourier transform, we know, and get a sequence of, again, capital T moving Fourier coefficients. Then in the next step, we use, okay, that was just how it was in our initial example. This was the sequence of Fourier coefficients. In the next step, we do the bootstrap, which means that we just use some standard frequency bootstrap methods and locally apply them to our Fourier coefficients. Well, you can find some of those bootstrap methods, for example, in Kirch and Politis. We use local versions of them, but we need, in order to use them, an estimate f hat of the time-varying spectral density. So the first problem is, can we find an estimator for that spectral density? Well, we use our moving Fourier coefficients and introduce a moving periodogram, like this, and then smooth it using just some kernel. And this f hat is our smooth moving periodogram. It's our spectral density estimator, and it's effectively just a function of one parameter, of k. But I think this notation is easier to understand. And what we need for this spectral density estimator to hold is, and what we have proved for this estimator to be true, is what we call locally uniform consistency. But what does that mean? We mean by that the true spectral density, for every point in time ut, the true spectral density at time ut and the estimated spectral density at time kt, and k is not really far away from ut, just plus minus m. But this difference goes to 0. So this is what we mean by locally uniform consistency. Well, and as I said, it's fulfilled for this estimator. We've proved that. And now we can apply wild bootstrap, residual bootstrap. Okay, so now we have bootstrap versions of those moving Fourier coefficients. We now can back transform them, and we use some moving version of the inverse Fourier transformation. And the construction is basically just like the moving transformation. It's picking a stretch of data, transforming, rearranging, shifting, transforming, rearranging, and so on. And then we get replicates back in the time domain. Well, this is quite some fancy procedure, but the question is again, does it work? The main theorem we've proved is that the moving TFT bootstrap actually manages to mimic the second order structure of locally stationary time series. And we have the assumption that time-varying autocovariance is absolutely summable, spectral density, Lipschitz continuous, bounded. We have this condition, this locally uniformly consistency. We have the bootstrap coefficients are centered, they are independent. And then we can prove that the bootstrap replicate at time ut and time ut plus h asymptotically equals the time-varying autocovariance at time u and leg h. And, well, this convergence is uniform in h, for h being less than m. For h being bigger than m, this is 0, because we have an m dependence of our bootstrap scheme. Okay, I know too much theory is a bit tedious, so let's look at some simulations. I simulated a time-varying autoregressive time series with coefficient minus 0.6, and it increases linearly to 0.6. And then I used the moving TFT bootstrap to produce replicates. I used the window width of, well, I used m equal 100, which corresponds to a window width of 201. And I got those, for example, those two replicates. And I think they look pretty good. Well, now we've thoroughly looked at this moving TFT bootstrap, which effectively uses that moving Fourier transformation. One could get the idea of maybe substituting those Fourier transformations that occur in the other bootstraps by the moving versions. Well, and this is what we did. We substituted this and called it moving autoregressive aided periodogram bootstrap, and we substituted here and called it, well, moving hybrid bootstrap. And we used those three procedures, and with their help, we constructed uniform confidence bands. And exemplarily, I did uniform confidence bands of the autocorrelation. So how did I construct them? It's actually quite a simple construction. You choose a lattice of points in between 0 and 1, take the time series, calculate the moving Fourier coefficient, then estimate the autocorrelation function at leg 1, and you do this for every point u in the lattice. And then you construct the confidence interval just by using this estimate plus minus some constant. Now the question is, how do we get this constant in order to make it a uniform confidence band, and in order to make it, I exemplarily picked 95% confidence band. Well, we get this constant by applying to our time series some of the, one of those 3 moving bootstrap procedures we've seen before. We get bootstrap replicates of those moving Fourier coefficients, and we do this capital B times. And for each of the sets of t coefficients, we again estimate the autocorrelation function. Well, what happens now? I just compare the bootstrap estimates to the original estimate. And for each bootstrap estimate, I maximize the distance to the original estimate with respect to u. And then in the end, I have capital B maximized distances. And I choose this constant c in a way that 95% of those distances are less than c, and 5% are bigger than c. Okay, so it's a very simple construction. Well, of course, I wanted to check that by simulations, and I'm going to show you some small excerpt from our simulations. Again, it's our time-varying AR process, same we've seen before. I used a time series of length 1000, m equal to 100. I did 500 bootstrap replicates, and I wanted to get some empirical coverage rate, and therefore I used 200 runs. And for generating innovations that are standard normal IID, the moving TFT bootstrap had an empirical coverage rate of 0.97. We constructed 95% confidence bands. The moving autoregressive aided parallelogram bootstrap, as well as the hybrid one, they had an empirical coverage of 100, which is a bit too much. Concerning chi-square distributed errors, we had 0.98, 0.99, and again 100. Well, looking at the confidence bands, you can see the dashed one is obviously the wild hybrid bootstrap. The dotted one is the moving autoregressive aided bootstrap, and the solid one is the TFT bootstrap. And this red line is the theoretical autocorrelation function. Another picture we have, again, the solid is the moving TFT bootstrap. That's our confidence band. Red one, theoretical autocorrelation. And you can see 2 realizations or 2 estimates of the autocorrelation function. That's a wiggly in here. Well, after I did this for the autoregressive processes, I also decided that I might look at some moving average processes. And I did that, same parameters, and I got those coverage rates. And I was shocked. Like, they were horrible. And then I looked at those pictures, which calmed me a little bit, because you can see the black curve is the true autocorrelation function. And basically, the only points where the confidence bands don't really cover the true autocorrelation function are those 2 edges. Just leave the beginning, and the end can be left. Just look at the middle part, these 2 edges. And I think, I haven't really worked on this window width. I just chose m equal to 100. So maybe we can somehow think of how could this window width be chosen optimally? Or maybe we could adapt it to the degree of change in this autocorrelation function. But these are just ways further work is going to take. So what we've seen so far is that the moving Fourier transformation actually closely mimics our local structure of our time series. Plus, it's numerically cheap, and we can, well, adapt frequency bootstrap methods to the locally stationary setting. We can also just refine some existing local bootstrap methods. And what's more, we can even get uniform, at least locally uniform results instead of just pointwise results. And we even assume that it's possible to correctly bootstrap spectral mean statistics using the moving version of the wild hybrid bootstrap. So all in all, I think the moving Fourier transformation is definitely worth a thought. Thank you.
Okay, having seen this for the first time really finished, I'm pretty overwhelmed. It seems we have solved a lot of problems that we are working on for years and years. Let me see what's the issue. The length m with respect to t certainly has to go to 0 in your asymptotic such that the spectral estimator is uniformly consistent. Can you comment a little bit on this? Because it's a pretty tough problem, even if your segments are not overlapping. Now you have a highly redundant moving average Fourier transform.
Well, could
A little bit of magic to me that this is going to work, but you checked it, I believe you. So what is the rate that you need that these things become, I think you need asymptotic independence in the end, right? You need to control that these things, because you have correlation, you have a pretty high correlation between the
we have
three.
asymptotically it's incorrelated, and we have the rate is m to the power of 3/2 over t goes to 0. So it's just the rate from Sergidis and Paparodidis I took, and it all went through with that rate. So it was just the first one I picked, and it all went through with it. So I was pretty happy with that.
And you can control the non-stationarity bias, the variance, and the classical bias with that?
Well, well, I can't. Like I can show this locally uniform consistency. I used the first part of the proof. I kind of used that argument from Franke and Herdle, who did this kind of split up thing with the supremum. Well, after I had this, it eventually all worked out. So this was the crucial part of the proof.
Great.
That's all, right? Any further questions?
Looking at the graph for your final example,
Yeah.
it would seem that the estimated, it would seem that the estimated values are biased with respect to the true value.
So
in that
they're just too low. Or
they need inflating. So there's a question therefore for the general method, is there an issue of bias? When you have an excursion, as you have here in the red lines, it is not fully followed by the estimate.
Well, well, you don't have like the part up to 200 and the part up like starting at 800. This is just because here I use some block method. So I just for the coverage rate, I just checked from 200 up to 800. This is how Sergidis did it as well. And I think when I'm in between this interval between 200 and 800, I don't know. I don't think it looks too low. I'm not sure, but
Yeah, the upper these are confidence intervals.
yeah.
Yeah. The white space between the upper confidence level and the lower confidence level is too far up where it is low, and it is too low when it is high. So it should go out further.
Okay, of course I'm rechecking on that. So
Yeah, but so there is an issue of biased results when you have an excursion in the autocorrelation function like that. It is not fully followed
okay.
by the estimate. It is partially followed, but not fully.
Yeah, but this kind of occurred only in this moving average case.
Yeah.
Like it worked fine for the autoregressive case.
Well, it would depend.
Yeah, of course.
I mean, that's a question about the specific example, but it could be generalized.
Yeah. Well, I certainly have to recheck on that.
Right. I think we should move on. Well, let's thank Francesca for this talk.